welcome back to our series of lectures on chemical bonding. Today we will take up valence bond theory. It is a modern theory of chemical bonding. The session is planned as follows, that is, to begin with we will briefly review the contents of previous sessions. Thereafter we will take up a qualitative description of valence bond theory, and having done that we will move on to what is called as the quantum mechanical description of valence bond theory. We will see that how do we describe this theory in terms of quantum mechanics. Thereafter we will outline the limitations of valence bond theory. Having done that, we will move on to introducing a concept called as hybridization. We will briefly touch upon this concept, which will be building up in the future sessions over there. Then towards the end we will try to sum up what we do in today's session. Now let us try to briefly review what we did in the previous sessions. What we did was that we started by introducing the concept of chemical bonding and gave a historical perspective of it. Thereafter we discussed two classical theories of chemical bonding, that is the Causal's theory and Lewis theory, and then thereafter we outlined their limitations. Having done that, we realized that these theories do not give any information about the geometry of the molecules. Then we brought in the VSEPR theory, that is valence shell electron pair repulsion theory, and by explaining this we use this theory to predict the geometry of different kind of molecules. Then towards the end we have discussed what are polar covalent compounds, then and how do we relate the polarity of a covalent compound with the percentage ionic character and things like that. So that is what we have done so far. Let us move further to make a case, to make an understanding of this valence bond theory. Let us recall two small things here. You remember that classically speaking that electron is considered as a discrete fixed unit of charge. There is a localized charge over there, and also the classical theories which we discussed in the previous sessions, they consider the formation of a bond to be driven by the stability of bonding atoms. That means suppose there are two atoms which have a certain stability. When the two come closer, if the stability of each one of them increases, then we say a bond formation takes place, and the stability is gauged in terms of the electronic configuration of the bonding atoms over there. On the contrary, if we look into the modern or the quantum mechanical view of atom, we know that the electrons are not discrete point charges. As against that, they are that the electron can be described in terms of a probabilistic region of space around the nucleus in an atom. So that is a one drastic movement from the classical to quantum mechanical description of an atom there, an electron in an atom. Because this is very pertinent, because we are going to take up the modern theories which primarily are based on the quantum mechanical view of atom there. The modern theories of chemical bonding, they are the ones which are based on the quantum mechanical behavior of atoms. That means we talk about the orbital picture of atoms there. There are two theories there. The first one is the valence bond theory, which we are going to take up today, and the other one is the molecular orbital theory, which we will be taking up in the future sessions over there. So there are two are the most important theories which describe the chemical bonding in terms of quantum mechanical behavior of atoms there. Now what is this valence bond theory? Valence bond theory, developed by Linus Pauling in 1930s, provides a very simplistic description of formation of a chemical bond. And if I want to qualitatively look into the bond formation, let us take the example of formation of hydrogen molecule from two hydrogen atoms. So according to valence bond theory, what we can see is that suppose I want to talk about the bond formation between two hydrogen atoms. So this is hydrogen atom 1, this is hydrogen atom number 2. So these two hydrogen atoms are shown as the electron as one as orbitals over there. So these two hydrogen atoms approach each other. When they approach each other, as they come closer and closer, these atomic orbitals, they overlap. That means these two atoms with their valence electrons in the valence orbital over there, they come closer and overlap with each other. When the two overlap, what happens is that in the internuclear region, because this is nucleus 1, this is nucleus 2, so between the two here we find that there is a increased charge density over here. You can see that these are two hydrogen atoms, these are the respective nuclei over there, and in the internuclear region we find that there is a increased charge density there. This increased charge density actually holds these two nuclei together, and we say a chemical bond is formed. So, that is a simplistic description of bond formation in terms of valence bond theory. Essentially, it amounts to saying that the bonding atoms they come close to each other in such a way that their valence orbitals overlap each other. Valence orbitals containing unpaired electrons overlap and form a bond over there. Let us look at another description of the same thing. Now, this basically is electrostatic potential maps depicting the formation of hydrogen molecule from two hydrogen atoms over there. And you will know that in electrostatic potential maps basically represent the atoms or molecules that basically represent the electron densities in the atoms and molecules over there, and they are represented in terms of the color differentiation. Kind of a blue coloration means low electron density, and red coloration means large electron density, and the green and yellow are in between the two. Now, what you see is that these two hydrogen atoms, when they are far apart from each other, so we find that there is a roughly equitable kind of a electron distribution there. When the two come closer, we find that this slight redness is developing over here, which basically is because of kind of a polarization of electron cloud towards the other nuclei. That means the nucleus of this atom, this nucleus here is going to pull electron of this atom towards itself. So, there is a slight polarization there. So, we can see that built up of a red coloration on both the tips over there. So, as the two come closer, they overlap. We find that in the internuclear region there is a large density of red coloration, which means there is an accumulation of electrons between the two in the internuclear region over there. This electron density which is built up over there, this holds the nuclei together, and we say that a bond is formed there. So, in other words, we can say that a chemical bond in terms of valence bond theory can be seen as a process by which there is an accumulation of charge density in the internuclear region of the two bonding atoms over there. So, that is one simplistic representation or a description of valence bond, formation of a bond by valence bond theory. Similarly, suppose I want to talk about formation of a bond, say a fluorine molecule over there. Now, what we can see here is that the two fluorine atoms, and these are the two p orbitals over there. That means the 2p orbital of this fluorine atom and the 2p orbital of this fluorine atom, the two come closer and they overlap. Here again we find that there is a built up of electron density in the internuclear region over there. Yet another example could be that of formation of HF here. So, in case of HF, what you find is that is in case of hydrogen, the valence orbital is the 1s orbital there, and for fluorine it is a 2p. So, this 2p of fluorine and then this 1s of hydrogen, the two overlap and form a bond over there. So, we find that this description is very straightforward and simple. Just the atomic orbitals, the valence atomic orbitals with unpaired electrons, they come closer, they overlap with each other, and the electron density in the internuclear region increases, and we say a bond is formed. So, that is very simplistic description in terms of valence bond theory. Let us move further and see that how do we describe this whole process in terms of quantum mechanics. We will not get into too much of details of this, but we will give a small description of this. We should recall here that the electrons in an atom exist in the atomic orbitals. We have been talking about it all these times here. Now, and we also know that the atomic orbitals are represented mathematically in terms of what is called as a wave function psi. Now that is about the atom here, but now we are talking about formation of a molecule from atoms there. Then how do we describe that? Once again, we will take the example of formation of hydrogen molecule from two hydrogen atoms there. To understand this, what do is we take two hydrogen atoms, say we call them as atom A and atom B over there. Now, with their electrons in the respective valence atomic orbitals, which we know that in case of hydrogen atom that the valence atomic orbital happens to be 1s orbital there. So, we designate them as 1s A just to say that this is 1s orbital of atom A. 1s B represents 1s orbital of atom B over there. Now, and then also we have used the two terms here, there is 1 and 2. 1 and 2 once again just indicative of here, they basically are descriptors of two electrons there. This 1 represents an electron belonging to atom A. 2 represents an electron belonging to atom B. It's just a notation there, otherwise all electrons are equivalent there. Now, when we say this 1s A, what does this 1s A indicate to us? This 1s A tells me that for this atom, this is the nucleus and this is the whole region where the electron can be located for a hydrogen atom A. Similarly, this tells me that this is the nucleus of atom B and this is the region where the electron can be located over there. Now, what happens is when the two approach each other, say this 1s A essentially is the wave function for this atom, 1s B is the wave function for this atom there. Now, when the two atoms approach each other, when they come close to each other, this entity here, the combined entity, that means a combination of these two atoms there, that can be represented in terms of a wave function which we call as psi 1 here as to be equal to 1s A1, 1s B2. What does it mean? What it means is that electron number 1 is in atom A, electron number 2 is in atom B and the two are close by, the two are together there in the neighborhood of each other. That is one representation of this kind of a combination of two atoms there. When these two atoms come close by, they are quite close to each other, the electrons are not distinguishable. We can't say this is electron 1, this is electron 2. Probably in such a situation, we can represent this combination of this kind of a combined effect of these two atoms in the neighborhood in terms of a wave function what is called as psi 2 here. Now, this psi 2 is given as 1s A2, 1s B1. What does it mean? This means that the electron number 2 which belonged to atom B earlier now is in the vicinity of in the domain of 1s A. That means it is in 1s orbital of atom A here. And 1s B1 means the electron number 1 is with the atom B over there. So, we find that since the two possibilities are there, the overall effect of these two possibilities can be put together in terms of what is called as psi VB or psi covalent to be equal to psi 1 plus psi 2. That means, if these two possibilities are there, then at this stage we can represent our wave function in terms of the combination of both the possibilities there. Now, let us understand what does this imply. This implies basically that these two psi 1 and psi 2 essentially represent covalent structures there, because if I look at this psi 1 here, psi 1 was 1s A1, 1s B2. That means, we can represent something like this. That means, atom A electron 1 with that, atom B electron 2 with that. So, two hydrogen atoms are in the neighborhood. So, it is a hydrogen molecule which is a covalent structure here as shown. Similarly, this also represents a covalent structure. So, essentially this particular wave function psi 1 plus psi 2 as we have just described here, that represents a covalent that is a wave function for a covalent bond formation between two hydrogen atoms. We will go a little further into this. If we try to imagine, we can realize that there are other possibilities there. The possibilities could be that we have 1s A1, 1s A2. What does this mean? This means that both the electrons, electron 1 and electron 2, both of them are in 1s A. Another possibility is 1s B1, 1s B2, which means that both the electrons A and B, 1 and 2 are in atom B over there, that is the 1s orbital of atom B there. Now, there are the possibilities, because when the electrons are moving, there are transient possibilities of this kind of things to happen. And if we try to analyze this, we find that these essentially represent ionic structures there, because when we say 1s A1, 1s A2, that means both the electrons are in atom A here. So, that essentially becomes hydride ion there, and since there is no electron on atom B over there in that case, so it will be basically hydrogen ion there. So, essentially this particular wave function represents an ionic structure of this kind. So, is true of this one. So, this also is this. See, if we can imagine both possibilities to be there, we can say that the psi ionic, that is the ionic component of this whole the argument we are trying to put forth here, can be represented in terms of something of this kind, that is psi 1s A1, 1s A2 plus 1s B1, 1s B2, so on and so forth. Now, what we see is that when the two atoms are there, atom A and atom B with their respective electrons 1 and 2, when they come closer, So, the combined effect can be put into all possible wave functions we have seen so far. Two of them were representing covalent structures. Now, these two are representing the ionic structures. If you put them all together, we can say that psi valence bond to be equal to psi covalent plus psi ionic. Now, so that is a kind of a valence, that is a quantum mechanical description, so to say, of the bond formation between two hydrogen atoms in this case over there. But what you find is that this description, though we are logically built up to this stage, we find that this does not sound very kind of acceptable over there, because what it says is that is the contribution of the covalent structure and that of ionic is roughly, they are equal, which is slightly beyond imagination, because okay, this we can't rule out these kind of structures, but we know that the common sense tells us that this is not going to be as probable as the covalent structures over there. So, we need to modify this particular description over there. So, they can be modified by doing some kind of a parameterization, wherein we take our psi valence bond to be equal to say some C1 psi covalent plus C2 psi ionic, which this C1 and C2 are coefficients which we can try to vary and try to see that which combination of these coefficients give me the best fit with the experimentation there. Simple way of looking at it could be that say this is about say 80%. So, 80% is psi covalent, 20% happens to be ionic, or maybe 90-10, 85-15 or 70-30 or whatever. That means we can try to keep the this component of ionic to be less and try to go on increasing it. We can do iterative procedures and try to find out what is the best combination over there. With all this, this probably is one simplistic way of looking at that how do we describe the formation of a chemical bond in terms of valence bond theory in using quantum mechanical jargon or the wave functions over there. Let us understand, having understood one simplistic qualitative description, two atoms with their respective valence electrons, they come closer, the orbitals overlap, the charge density increases, we say bond is formed, that is qualitative. And in terms of quantum mechanics, we have seen that this whole process can be expressed in terms mathematically in terms of the wave functions, and we have seen how do we logically build up those wave functions there. This valence bond theory though gives a very simplistic kind of a view of bond formation, it has got certain limitations, and the limitations happen to be, firstly, it does not explain the geometry or the structure of a polyatomic molecule, because I mean because we just described hydrogen molecule or any other, because we have taken three molecules here, one was hydrogen, one was fluorine, one was HF, all the three of them happen to be diatomic molecules. So, in case of diatomic molecules, two atoms A and B, they come together, they form a bond. So, by by default the molecule happens to be linear, but if when you go to polyatomic molecules, we find that say molecule of water, ammonia, methane, so you find that all these polyatomic molecules have got certain geometry, and valence bond theory does not give any clue or any indication about how to talk about the geometry of these molecules there, and for that we have to bring in the concept of hybridization, which we will be taking up in a short while from now. The second drawback of valence bond theory is that it incorrectly predicts oxygen molecule to be diamagnetic in nature. Let us understand that. Basically, what we have seen so far is that in case of valence bond theory, the two atoms which are going to combine, when they come together with their unpaired electrons in the valence shells, they come closer and these get paired up. So, any bond formation will lead to a pair of electrons there. So, in case of oxygen molecule also, since there are two bonds formation there, two bonds are formed there, and that means there will be two pairs of electrons formed in that. That means there will not be any unpaired electron. Since all the electrons will be paired up, this molecule of oxygen is going to be diamagnetic in nature, whereas experimentally we find that oxygen happens to be paramagnetic. So, here this is the point where valence bond theory kind of fails or is inadequate to explain the experimental observation there. So, this aspect we will take up in the next session, but for right now we will try to introduce the concept of hybridization. Let us see that how do we reconcile, that means how do we build up on this basic concept of valence bond theory and see that how do we accommodate or how do we explain the shapes of different kind of molecules or the geometry of different kind of molecules using a concept called as hybridization. We will take the example of a simple molecule like beryllium dichloride. Beryllium dichloride is a simple molecule which happens to be linear. Now, in order to understand the concept of hybridization, let's build up from the scratch. Let's see that if I want to talk about a formation of this molecule or formation of bond between the beryllium and two chlorine atoms, we start with writing down or talking about what is the electronic configuration of beryllium atom, and we know that that happens to be 1s2, 2s2. We can represent it in this particular way, which essentially tells me helium core here, which essentially is 1s2, because we know the electronic configuration of helium is 1s2. And this 2s2, these two electrons in the 2s orbital are shown like this. That means there are two electrons in the 2s orbital there, and the 2p orbitals happen to be empty there. Now, with this kind of electronic configuration, we find that there are no unpaired electrons. Since there are no unpaired electrons, so we do not expect any bonding according to the valence bond theory, because we remember that when for the bond to be formed according to valence bond theory, the contributing atoms must have unpaired electrons which come together and get paired up there. So, in this case, we expect no bonding to be there, but we know that the beryllium dichloride does exist. So, the question is, how do we explain this kind of a bonding there? In order to explain this bonding, Linus Pauling, he proposed that to understand this, to explain bonding in beryllium dichloride, we can propose that one of the 2s electrons gets promoted to a 2p level there. That means we got a 2s electron there. So, if one of these electrons gets promoted here, and what we have is the following electronic configuration there. That means this core remains as intact, and there is one electron in the 2s orbital, one in the 2p orbital over there. Now, with these two unpaired electrons, now we expect that there can be formation of two bonds as desired for this molecule to be formed. But there are two small questions over there. That means for this promotion, because all this there some kind of energy is required for this, and Pauling argued that this energy which is required for promoting an electron from the 2s orbital to 2p orbital is more than compensated by the formation of bonds. That means once the bonds are formed, because formation of bond is going to liberate energy. So, that energy will be more than what is required for this to be promoted over there, some kind of a logical rationalization of this particular thing. But the question is, have we really been able to solve our problem? The answer is no, because this particular kind of a proposition that one of the 2s electrons gets promoted to 2p orbital only partly solves the problem. It solves the problem in the way that there are now two unpaired electrons which can lead to formation of two bonds. But what happens is, these two bonds which will be formed will be of different nature. That means, say one of the bonds will be formed by the overlapping of 2s orbital of beryllium and 2p orbital of chlorine atoms there. So, that is one bond, whereas the second bond will be formed by 2p orbital of beryllium and 2p of chlorine, because chlorine orbital is fixed, because that is the valence electron happens to be the 2p orbital there. But the two unpaired electrons which you have been able to generate by promoting the 2s electron to 2p, they happen to be in two different orbitals there. So, thereby the two bonds which will be formed will be different, but we know experimentally that these bonds are not different. So, our problem is partly solved, that we were able to accommodate formation of two bonds, but we are not able to explain that how do we reconcile with the idea that these two bonds happen to be identical, equivalent. So, to circumvent this problem, to get over this problem, Pauling further proposed. He proposed that once we got these two electrons which are unpaired, that this 2s orbital and one of the 2p orbitals are mixed together to give rise to two new orbitals called as sp hybrid orbitals. Let us understand that. What we had achieved so far was that we got two unpaired electrons, one in the 2s orbital, one in the 2p orbital there. Pauling says that these two orbitals mixed together, they hybridized, they mixed into one another and gave rise to two new orbitals which are called as hybrid orbitals. They are designated as sp, because one of s orbital is involved, one of p is involved there. So, we generate two orbitals which are called as sp hybrid orbitals. They will have energies less than that of p, more than that of sa, somewhere over here. and these two both of these orbitals here, which have been now formed because of combination of these two orbitals there, they happen to have energy which is intermediate between these two, and also they contain one unpaired electron each there. Since these hybrid orbitals are equivalent, now that problem of two bonds to be not identical, it's taken care of, because now the bond formation, further bond formation or formation of molecule can be seen in the following way. That is, we had 2s orbital there, 2p here, these two mixed together, they give rise to hybrid orbitals called as sp hybrid orbitals. The two put together kind of shown like this is beryllium there, this is one of the sp orbitals there, this is second sp hybrid orbital there, and these two are diagonally opposite to each other. So, these resulting hybrid orbitals consist of a large lobe pointing in opposite directions as shown over here. That is, the hybrid orbitals contain one unpaired electron each. With this situation, the formation of bond, formation of molecule becomes very straightforward, and that can be shown as, that is, this sp hybrid orbitals on the beryllium atom now overlap with the 3p orbitals of the chlorine atoms to give the molecule. That is how do we represent that. That means, we had a beryllium atom with two hybrid orbitals over there, that is called as sp hybrid orbitals, one of the 3p orbital of chlorine atom, and this is of the second chlorine atom. The two overlap with respectively with the sp hybrid orbitals and give the desired molecule beryllium dichloride, which has got two bonds now. This is beryllium chloride bond here, BeCl bond over there, and both the bonds happen to be equivalent because our sp orbitals are equivalent over there. So, since the hybrid orbitals are equivalent, the two bonds are identical, and so this way, by invoking the concept of hybridization, firstly proposing that there is a kind of a promotion of an electron from a given orbital to another one. So, that takes care of the number of unpaired electrons required, and second thing is that these orbitals having unpaired electrons can combine together to give rise to equivalent orbitals, which then form the bonds with the second kind of atoms over there. This hybridization is not a physical phenomenon. It is not that something physical is happening over there, it basically is a mathematical operation. It is such that it allows us to describe the electron distribution about a bonded atom in such a way that it accounts for the geometrical shape of the molecule which are experimentally observed. So, it basically is a mathematical operation which helps us understand or explain the experimentally observed geometrical shapes of the molecules over there. So, it is a theoretical concept. Let us see that what is the rationale, or what is the rationale behind this concept of hybridization. We can put them together like this. We know that the polyatomic molecules, as we just seen with one example over here, they have got certain shape or a geometry. This geometry can be obtained if the orbitals which are involved in the bond formation are suitably oriented, and we know that these available atomic orbitals may not have the required orientation, as we just saw in case of our beryllium dichloride there, because s orbital here, the 2s orbital was spherical, whereas p orbital happened to be aligned along a given axis, say z axis over there. So, they were not having suitable orientations there. So, in order to circumvent this, in order to overcome this problem, we take a suitable combination of these atomic orbitals which are there on the atom over there, and generate orbitals which are the ones which provide the desired orbitals which are suitably oriented in the space in such a way that the desired geometry of the molecule can be explained over there. So, that is a kind of rationalization there, that is, the orbitals which are available on the atom, they are not suitably oriented. So, we mix in such a way, mix these orbitals in such a way that we get hybrid orbitals which are suitably oriented. So, that is the rationale behind this concept of hybridization. We will talk more about it in the next session there. Let us sum up what we have done today. What we have done today is, we started by reviewing the contents of the previous session. Thereafter, we gave a qualitative description of the valence bond theory or valence bond approach as it is called, that is, how does the formation of a bond take place according to valence bond theory. Thereafter, we explained the valence bond theory in terms of quantum mechanical description, that is, we used the wave functions for the contributing atoms and saw that how these wave functions combine together to give a wave function which describes a molecule as against the atoms which are contributing to the formation of molecule there. Thereafter, we outlined the limitations of valence bond theory, and towards the end we introduced the concept of hybridization there, and this concept of hybridization will build up in the next session there. Thank you.